Thanks for coming, everyone. We are Chimera. Uh, Chimera is an open source tool for performing automated canary deployments of containerized microservices that communicate via a service mesh. In this presentation, I'm going to start off by giving just a quick breakdown of microservice architectures, and then I'll take a look at what deployments look like in these type of systems before going deeper into canary deployments specifically. I'll then pass it along to Wes, who's going to talk about some potential solutions that containerized microservices can use to perform canary deployments, and then to talk about what makes Chimera unique amongst those options. We'll then pass it to Will, who's going to talk about what it's like to use Chimera and give a quick demo, and then Josh will explain some of the challenges we faced and the trade-offs we made while building Chimera, before going into the directions that Chimera may go in the future. So first, I'm going to talk about microservice architectures. This is a type of design where the major parts of your system are broken out into isolated applications. Those applications communicate internally by making network requests to one another. Managing these lines of communication is one of the most difficult parts of having a microservice architecture. However, there are some tools that help to simplify this for a developer. One such tool is a service mesh. This abstracts away all of the complex logic of traffic routing and inter-service communication. And by setting up your service like this, it allows each of your microservices to be managed, to scale, and to update without having to worry about how it's going to affect any other part of the system. And that's really important when we start talking about deployment. By having a microservice architecture, it allows you to follow this concept that's known as CI/CD. This stands for Continuous Integration, Continuous Delivery. This is a process where your code is in a constant state of being updated, and as frequently as possible, you are pushing those changes to production. What's important to note about this process is that updating the code is only actually half of the process. The other half is deployment. And because these deployments are happening frequently, it's a process that has to be seamless, and it has to be able to pick up on and handle any errors that pop up during the process. No matter how thorough a development testing suite is, there's always a chance that there's going to be unforeseen errors that show up when that code is pushed to production. Your deployment process has to be able to handle that quickly. A traditional approach to deployment would be known as an all-at-once deployment. This is where at a designated time, you take your application offline, you update it to the new version of the code, and then once that's running, you put it back online. While this is simple, it does introduce some potential issues. The first issue is downtime. Availability is one of the primary concerns of a modern application. If you're doing an all-at-once deployment, you're sacrificing availability to get your new code online. And if you're talking about doing continuous delivery, this means potentially taking your app offline several times a day. The second issue is errors, or more importantly, how many of your users are affected by errors. An all-at-once deployment means that all of your code has been switched over to the new version, which means 100% of your users are going to be affected by any errors. And that leads to our third issue, which is rollback. If there's an error that's too big to be fixed in production, it means you're going to have to roll back to the last stable version of your application. And with an all-at-once deployment, this is essentially another full deployment process with more downtime. There's a few popular solutions that address some or all of these issues for companies that want to do continuous delivery. First, I'm going to look at blue-green deployments. This is a process that involves first spinning up a whole new environment to host the new version of your application. Traffic continues to flow to the old version while that new version is starting up. Once it is started up, you're able to shift 100% of your traffic over to the new version. The old version remains active while you monitor for errors. If anything goes wrong, you can quickly switch 100% of your traffic back to the old version. This is a good solution, but there are some downsides. First, you have two full environments running, so you have to deal with the costs associated with that. And second, since all of the traffic is going to that new version, that means 100% of your users are affected if there's any errors. Next, we'll look at rolling deployments. This can be used if you have a horizontally scaled application where you have multiple instances of your app running to handle large amounts of traffic. A rolling deployment involves updating each of those instances one at a time. So first you spin up a new instance with the new code, and then once that's up and running, you take down an old version of the code. If there's any errors, only the users who end up directed to that new instance will be affected by it. Plus, you're saving on costs because you're not duplicating your entire environment. The downside here is with rollback. If you're late in the deployment process, most of your old stable versions are no longer running. So a rollback means that you're going to have to wait for all of those to start back up before your application's back to full capacity. And this may mean you end up facing availability issues. So now let's look at canary deployments. First, you spin up a new version of your application, and then once that's running, you put a load balancer in front of the new and the stable versions, or you reach into whatever routing tool your infrastructure is currently designed to work with. You then shift a small portion of the traffic over to the canary version, and once it's receiving traffic, you monitor it for errors. If there is an error, you can switch 100% of the traffic back to the stable version of your application. Or if everything's satisfactory, you can slowly shift more and more traffic over to the canary and monitor at each step. Once 100% of the traffic is going to the canary version, you can take down the old version with confidence because you know that the new version can handle the load. If there's any errors, only a small number of your users are affected early in the deployment, and no matter where you are in the deployment process, the rollbacks are always fast. The downsides of canaries, again, you have 2 full environments running, but more importantly, when talking about continuous delivery, this is a complex process with a lot of moving parts that will need to be automated if it's happening frequently. To see how this process looks for containerized microservices, I'm going to break it down into a couple of different components. First, at the core of this is where your applications are living. For containerized microservices, this is going to mean interacting with some sort of container orchestrator like Kubernetes, Docker Swarm, or Amazon's Elastic Container Service, or ECS. These are tools that help a developer to deploy their application, manage the compute resources that the application is running on, and configure how those resources should scale. In a canary deployment, this is where you're going to control the deployment of the canary version and the tearing down of a version at the end of the process. Next, we'll look at a traffic routing tool. This is going to be a load balancer or some sort of infrastructure tool that handles your routing. For Chimera, this is where that service mesh comes into play. Remember, that's the tool that's used for managing communication between microservices. Most service meshes include what's called a virtual router. This is a tool that dynamically directs traffic based on your instructions. In a canary deployment process, this is what will be adjusted to slowly shift the traffic over to the canary version. The third component here is a monitoring tool. This is a service that tracks the health of the canary. It's usually going to be pulling in some sort of time series data to monitor things like latency, compute resources, and any errors that your canary is returning. The final piece here is some sort of canary management tool. This is a service, or if this process is being done manually, this is a developer that has to use the container orchestration tool to deploy the new version of the application, manipulate your traffic routing tool, and then monitor and make decisions based off of whatever the metrics tool is returning. I'm now going to pass it over to Wes, who's going to break down what options are out there for containerized microservices that want to automate their canary deployments, and to see how Chimera fits into that picture.
Thanks, Trevor. So to start this part of the talk, we will look at some of the current automated canary deployment tools for containerized microservices. Generally speaking, there are a few distinct categories, and we'll briefly look at each of them one by one. The first kind of automated canary deployment tool is Kubernetes-centric. Kubernetes is still the most popular container orchestration tool, so it's no wonder that many automated canary deployment tools work exclusively in the Kubernetes ecosystem. Even though these tools are limited to a Kubernetes-type container management system, they are typically quite flexible regarding the traffic routing tools and monitoring tools with which they integrate. Kubernetes-centric canary deployment tools are open source, which means you can usually tell how they work, or in other words, why they would promote the canary service or not during the canary analysis stage of deployment. Moreover, as long as you already work within the Kubernetes ecosystem, these tools are easy to set up and use. However, if you're using a container orchestration system like AWS's Elastic Container Service or Docker Swarm, then these tools are not available to you. The second category is the ultra-flexible open source solution. These solutions work with just about any chosen combination of container orchestration, traffic routing, and monitoring tools. This is often because these solutions are themselves large collections of freely configurable microservices. However, the trade-off for maximal flexibility is that these solutions often come with the daunting challenge of configuring their microservices and using them alongside your current microservice infrastructure. The third category is the CD as a service platform. These products offer continuous delivery and deployment as a service. They offer a streamlined experience that abstracts away much of the setup and operational complexity of the flexible open source options that we just discussed. Although CD as a service solutions are easy to get up and running out of the box, these tools are typically quite feature-rich and flexible, and that generally implies that competent usage requires some expertise and experience. Finally, CD as a service platforms are not as transparent as open source solutions. It is often difficult to interpret how they work or why they would continue rolling the canary forward or roll it back. This is because their internal infrastructure is inaccessible to the user, and they sometimes use unsupervised machine learning tools that lack transparency by design. So let's summarize the landscape of automated canary deployment tools for containerized microservices up to this point. First, we have the open source Kubernetes-centric tools, where the simplicity of their usage depends on whether you're already working within the Kubernetes ecosystem. Second, we have ultra-flexible open source solutions. Their tremendous flexibility often comes with the cost of additional complexity. Finally, we have the CD as a service platform. These are often quite flexible solutions, but their inner workings are inaccessible. Moreover, the simplicity of their usage depends on whether you're using default settings or making fine-grained configurations at every opportunity. Generally speaking, what is missing is an open source, easy to use solution that simply works for those outside the Kubernetes ecosystem. And that is why we built Chimera. For the rest of this part, I will introduce Chimera's central features before passing it on to Will, who will give you a better indication of what it's like to be a Chimera user. To introduce Chimera, it is helpful to recall that canary deployments for containerized microservices involve a container orchestration tool, a traffic routing tool, and a monitoring tool. So where's Chimera's place in all this? Well, these components are neither individually nor jointly sufficient for automating canary deployments. As Trevor made clear, a specialized tool needs to integrate with these other tools to automate a canary deployment. Every automated canary deployment tool shares that in common, and in that sense, Chimera is no different. But to see how Chimera in particular works, let's take a look at how Chimera integrates with each of these components taken one at a time. To start, let's look at which container orchestration tool Chimera supports, and we'll slowly build out from there. So rather than Kubernetes, you can currently use Chimera for containerized microservices managed by AWS's Elastic Container Service. On the right, you can see a stable version of a task surrounding a stable version of your containerized app. The basic idea here is that the currently stable container is part of a group of one or more containers that share compute resources that the task manages. Furthermore, ECS is responsible for deploying the task, scaling it out, and registering it under a subdomain. Because Chimera automates canary deployments, it automatically deploys canary versions of your service by controlling some of these managerial features of ECS. In particular, when given an updated container image of your service, Chimera instructs ECS to deploy your canary task, which in turn runs your containerized canary app. Importantly, ECS can deploy containerized services in one of two ways: Elastic Cloud Compute or Fargate. Fargate is a compute resource where AWS manages the compute instances upon which your tasks run so that you don't have to. And currently, Chimera only supports ECS for container management with Fargate deployment. Next, you can use Chimera for automatic traffic routing for infrastructures currently using AWS's managed service mesh, which is called app mesh. Like other service meshes, app mesh consists of virtual components that abstract away the fine-grained details of inter-service networking, load balancing, and service discovery. Virtual nodes, for example, are best thought of as pointers to ECS tasks. App mesh uses the configurations of virtual nodes to configure an Envoy sidecar proxy on ECS tasks. These sidecar proxies intercept all traffic to and from the application container and apply the appropriate network communication rules. Another abstraction of service meshes and app mesh in particular is a virtual router. App mesh uses a virtual router's configuration to split traffic through weights. In this way, it's like an abstraction over a traditional load balancer. Because virtual nodes correspond to ECS tasks, Chimera also automatically deploys a CANARY virtual node and a containerized Envoy proxy during the first stage of the CANARY deployment. This is necessary for Chimera's control over traffic routing to propagate down to the actual containerized services. During the traffic routing stages of a CANARY deployment, Chimera reaches out to app mesh's control plane and automatically modifies the weights of virtual routers to shift the traffic from the stable service to the CANARY. For monitoring metrics, Chimera currently uses AWS's CloudWatch. Chimera deploys a Prometheus configured CloudWatch task into the user's ECS cluster. The containerized CloudWatch agent of that task uses Prometheus to scrape error response metrics from the CANARY's Envoy proxy. The CloudWatch agent then stores that time series data on CloudWatch. Chimera checks the CANARY's health based on these metrics every minute. In particular, Chimera automates CANARY analysis by checking whether the metrics are above or below a user-defined threshold value and decides whether to promote the CANARY based on that threshold analysis. Finally, by controlling app mesh and ECS, Chimera also automates tearing down relevant infrastructure. So suppose the CANARY service succeeds and becomes the new stable version. In that case, Chimera automatically removes the old virtual node from the virtual router's routes, removes that virtual node, and removes the relevant ECS infrastructure. On the other hand, if the CANARY service fails, Chimera automatically ensures that all the traffic is routed back to the stable version and tears down all the CANARY-related infrastructure. Now, before getting a better idea of how a developer uses Chimera, let's see where Chimera fits within the landscape of automated CANARY deployment tools. Currently, Chimera is limited in certain respects. If your containerized microservices do not use either ECS or app mesh, then Chimera is not the right fit for you. However, Chimera is an excellent tool for those whose containerized microservices are orchestrated by ECS and communicate via app mesh. Moreover, it's open source and provides easy to understand CANARY analysis. And finally, as will demonstrate, getting Chimera up and running could not be simpler.
All right, thanks, Wes. So now I'm going to show you what using Chimera is like from the perspective of a developer. So Chimera was designed to simplify the deployment process, and its introduction into a developer's workflow should accelerate the deployment process while also reducing the cognitive overhead required to do so. And therefore, it was critical that the installation and usage of Chimera be a familiar and streamlined process for any developer. So to accommodate this requirement, our team chose to Dockerize Chimera. And that way, the developer needs to only have Docker and Docker Compose installed on their local system. Docker Compose is then used to build the images for an Nginx served front-end React app and a Node.js Express backend. And this simple installation process allows Chimera to be deployed locally or in the cloud based on whatever the developer's needs may be. Once installed, performing CANARY deployment with Chimera is just a streamlined process presented step-by-step through a simple web app that's accessible on the local host. So to best demonstrate this, I'm going to walk you through the process using our dev team's logo app as an example. So here you can see that the logo app is a simple microservice that returns a black and white logo whenever the page is refreshed. And our developers have been hard at work on a new color version of this microservice, and now it's time to deploy it. But this app is just one of many microservices on their infrastructure. And as such, it's an ideal candidate for a CANARY deployment. But manually performing a Canary deployment in a complex environment such as this is both time consuming and prone to error. And then although our devs are great at making new logo apps, they're not experts on service meshes, container orchestration, and metric analysis. And therefore, they're going to use Chimera for deployment. And to do so, they'll provide their AWS credentials and some basic infrastructure information. Chimera is then able to query AWS for extensive details on their existing infrastructure and configuration settings. And it's going to be able to leverage this to provide the developers with the minimum number of decisions and options that they'll need to make in order to successfully perform a Canary deployment. There is a one-time setup process that's going to prepare the existing infrastructure to work with Chimera. The developer just needs to define a namespace that's going to be used for metric collection and provide an AWS virtual private cloud ID. And this is going to place an agent on their infrastructure that's used to scrape the metrics required by Chimera to perform Canary deployments. But once this is complete, their infrastructure is now ready for Chimera to perform a Canary deployment to any of their services. So to start, they're going to provide, they'll be provided with a selection of services on their infrastructure, and the developer simply chooses the candidate service for deployment. In this case, it's going to be logo 1. And they're going to provide a name for the new service being deployed. Here, it's going to be logo 2. Chimera is then going to query AWS and provide a tailored set of options for configuration. And because every infrastructure is different, Chimera attempts to minimize the number of assumptions it makes while still providing clear and simple steps for configuration. So for new infrastructure, the developer needs to provide custom details, starting with a new task definition family. The URL for the Docker image where the new application can be found, and then a new virtual node. Configuration settings based on existing infrastructure are selected from predefined lists created through queries to AWS. And finally, the Canary deployment itself can then be customized by the developer through setting up the interval length over which traffic is shifted, the amount of traffic shifted by each interval, and the metrics which are tolerable for deployment to continue. And now we get to the fun part where we actually get to deploy our Canary service. So the deployment phase is going to begin with preparing infrastructure for the new Canary service. The control plane for the service mesh is updated with a new virtual node that acts as an endpoint for intra-mesh communication to the Canary. And the Canary is defined with a new task definition, including Docker images for both the application and the envoys. One or more instances of the tasks are going to be spun up with containers for both the applications and the envoys. And then at this point, Chimera is going to have to wait for these new changes to propagate and the Canary services to be fully discoverable by the service mesh. So here you can see our devs clicks begin deployment and Chimera gets to work. They can see as the virtual node, task definition, and ECS services are created, and then Chimera pauses to wait for the service discovery changes to propagate. And at this point, 100% of the users are going to be directed to the version 1 of the logo app. And refreshing the page is always going to return back this black and white logo. So when Chimera does receive confirmation from AWS that the changes have fully propagated, traffic can start to be shifted to the Canary. Chimera is going to shift traffic by adjusting weights used by virtual routers in the service mesh. And based on the previously configured input from the developer, a percentage of the traffic is directed by the virtual router to the new virtual node representing the Canary. Chimera's status updates once the ECS service is ready, and a percentage of the traffic is shifted from the stable, the black and white app, to the Canary or color app, so you can see here. And now, when the page gets refreshed, roughly 50% of the time, a user is going to be directed to the original black and white logo. And 50% of the time, a user is going to be directed to the new color logo. And every minute, Chimera is going to be comparing the metrics that were generated by the Canary against that previously defined tolerable threshold. And at the end of an interval, if the metrics are satisfactory, the next interval begins, and a greater percentage of the traffic is going to be directed to the Canary. And this is going to continue until 100% of the traffic is directed to the Canary for an entire interval. And at the end of this final interval, if the metrics are still satisfactory, the deployment is a success and cleanup begins. But if at any time the metrics are unsatisfactory, Chimera is going to recognize this deployment as a failure. And so here you can see there appears to be a bug with our new color logo app, and users are occasionally experiencing 500 errors where no logo is being returned. So what happens when there's an error? Well, Chimera detects a failed deployment, and it instantly begins rolling back to the original service and infrastructure. And all traffic that's currently directed to the Canary is immediately shifted to the original service. The virtual node task instances and definitions of the Canary are torn down and removed. So here you can see our dev watches as there's a spike in 500 errors appearing in the Canary health chart. So Chimera recognizes the failures and automatically begins rolling back the infrastructure to the stable black and white logo app. And our devs can rest easy knowing users can continue to access the original black and white stable version of the logo app. So when deployment does succeed, Chimera begins cleaning up the old service in a process that's very similar to the rollback of a failed deployment. So it's going to tear down and remove the virtual node task instances and definitions of the original service, the black and white logo app. So here, our devs watch as the Canary health metrics indicate a successful deployment. And all traffic is now directed to the Canary, the color logo app, and the stable node services and task definitions are removed. Now, all users are directed to the color version of our logo app, and the black and white logo app has been safely removed from the infrastructure. Our devs can now get back to work and focus on their new blockchain version of the logo app. So by amalgamating all the required options and predefining as many selections as possible, Chimera vastly simplifies the process and greatly reduces the potential for developer-introduced errors during deployment. And I can speak to this personally, having tried to deregister a task definition after a manual Canary deployment. And as my team watched on, somehow managed to delete my entire microservice architecture. So this is just one challenge we faced while designing Chimera. And to talk to you further about the design decisions and challenges that went into creating Chimera, I'm going to turn things over to my teammate, Josh.
All right, thanks, Will. So I'm going to talk about some of the challenges and design decisions that we faced while building Chimera. And then I'll wrap up by talking about some additional features that we would like to add to Chimera in the future. Then we'll open it up to any questions you might have about Chimera. So before I talk about the technical challenges, I'd like to walk through some of the design principles that we kept in mind while designing Chimera. So the first of these principles was ease of use for the end user. It was important for us to minimize the amount of configuration that we required from the user, and we wanted the process of using Chimera to be transparent and for it to provide clear and understandable results. We also wanted to design Chimera so that it would have a minimal impact on the user's existing infrastructure. AWS resource configuration can be very complex, so we wanted Chimera to modify these resources as little as possible, to reuse existing configuration options, and to introduce as few new resources as possible into their infrastructure. So with those principles in mind, one of the early design decisions we faced was how Chimera would actually interact with AWS. We evaluated several options, and we decided against using third-party tools like Terraform for the sake of simplicity. We wanted to avoid introducing too many separate tools or other solutions into the project. So that left us with the options provided by AWS, specifically CloudFormation, the Cloud Development Kit, and the Software Development Kit. CloudFormation and the Cloud Development Kit are both infrastructure as code options. CloudFormation allows you to deploy AWS resources by providing template files that describe your intended infrastructure. And the CDK is closely related to this. It's a library that is available for several programming languages that allow you to actually design the infrastructure using a familiar programming language. The CDK can then be used to synthesize and deploy CloudFormation templates. The Software Development Kit, on the other hand, is a bit more conventional. It's a library provided by AWS that allows you to interact with AWS resources directly in your code using a familiar programming language. So we chose to use the Software Development Kit, and there were three main reasons for this. The first is that it allows us to create and configure AWS resources whenever we need to as the Canary deployment is being performed. Second, it allowed us to pull metrics directly from AWS CloudWatch to determine whether the Canary is healthy or not as we go through each stage of the deployment. And third, it allows Chimera to determine when each phase of the CANARY deployment can start and end based on the results of queries to the AWS resources. For example, when we need to wait for the new services to be discoverable so that we can actually route traffic to it. In addition to these three things, the SDK also gave us the ability to hold true to our overall design goals. A good example is that using the SDK gave us an easy way to reuse existing configurations anywhere we could. With the SDK, we can pull down the exact configuration of an existing service and then modify only the options that Chimera needs, and then deploy an almost exact replica of that service running a new version of the code. This, in addition, helped us reduce the configuration input that we required from the user. Usually given just a few names describing those resources, we could use the SDK to find most of the information that Chimera needs to do its job. So once we understood how Chimera would communicate with AWS, the next challenge was determining how Chimera would collect the metrics for the new service it deploys. We knew from the beginning, and I've mentioned before, that we wanted to take advantage of CloudWatch because it's an observability and monitoring service provided directly by AWS. But getting the information that we needed into CloudWatch was the hurdle that we had to actually address. Because our user's infrastructure is running on AWS Fargate, we don't have access to an underlying machine, and therefore we can't use any operating system level tools to collect metrics or networking information. Instead, we have to rely on what is made available by ECS and by the data plane of our service mesh, which in this case is the Envoy proxies that are attached to each service. So fortunately, AWS provides a containerized application called the CloudWatch agent, which can be used to collect metrics from the Envoy proxies and then export them to the CloudWatch platform. In order to do this, the task definition of each ECS service must be updated to include the CloudWatch container. This solves the problem of collecting metrics from the proxies, but it wasn't in line with one of our design goals because it requires reconfiguring multiple services and adding several new components into the user's infrastructure. So to address that problem, we decided to instead use Prometheus to collect metrics from the Envoy proxies. Prometheus is a monitoring service that can be configured to scrape the proxies at regular intervals and collect specific metrics. A single CloudWatch agent that's been configured to use Prometheus can be deployed directly onto the user's ECS cluster, and then Prometheus will handle the task of scraping the proxies, and then the CloudWatch agent running in that same service will handle exporting the collected metrics to CloudWatch. So doing it this way greatly reduced the complexity of the infrastructure that Chimera needs to create, and it has very little impact on the user's existing infrastructure. So now that we knew how we would collect the metrics, the next choice was which metrics would be considered when deeming a service healthy or unhealthy. So we began this decision by considering what's commonly referred to as the 4 golden signals, which are saturation, traffic, latency, and error rate. So we evaluated each of these and we considered how their inclusion in Chimera's health checks would impact our guiding principles. So first was saturation, which is a measure of the amount of available system resources that are actually being used. This is an important metric because the performance of a system can degrade even before it reaches maximum capacity. But it can also be a complicated metric because there are several kinds of resources to consider, like CPU, memory, and storage. And on top of that, which resources are relevant is also dependent on the nature of the application. So for that reason, we decided that Chimera would not consider saturation for health checks because including it would require either more complex user configuration or Chimera would have to be more opinionated and potentially less transparent about the deployment process and the results of that process. So the next signal is traffic, which is another way of considering the system's use of available resources. This is instead commonly measured as the number of HTTP requests sent to the application per second. And this metric comes with complications that are similar to those of saturation. The nature of the application will dictate what constitutes a useful measure of traffic. For example, certain streaming applications may be more interested in network I/O rate rather than a simple number of connections to that service. So for that, similarly to saturation, we decided that Chimera would not consider traffic for health checks. So that left us with latency and error rate. And latency is the measure of the time required to handle a request, and error rate is a signal that measures the amount of requests to the service that fail. And failure can mean a lot of things depending on the task the service is supposed to perform, but in many cases, simply capturing all HTTP 500 requests is sufficient. In other cases, this might involve end-to-end testing to actually determine whether the content of the response is what was expected. So we decided for Chimera that error rate would be the primary health check metric. A key benefit of using Canary deployments is to minimize the amount of users that can be negatively impacted by errors in new code. And we felt that tracking error rate was the signal that's most closely aligned with that goal. And in keeping with the design goals of simplicity and ease of use, we decided that Chimera would just track the number of HTTP 500 status codes returned by the service. This keeps Chimera configuration simple because the user can define a basic threshold, and if the number of failures exceeds that threshold, Chimera can initiate an automatic rollback. So another big decision that we faced was which strategy would Chimera actually use to perform Canary deployments. A common strategy involves comparing the performance of the new version with a copy of the production environment, which we call the baseline. The baseline will have the same version and the same configuration as the production deployment, but it'll be deployed at the same time and in the same way as the Canary that's being tested. And the reason this is useful is because you can minimize factors that don't involve new code from skewing the results of the comparison. For example, if you compare a brand new version of a service to a version that's been running for a while, issues like cache warm-up can make it seem like the Canary is underperforming when it's really not. So we decided that it was not worth the added complexity of using a baseline, specifically because of the fact that Chimera works with systems running on Fargate. Even if Chimera does deploy a baseline, it doesn't actually have control over when that service starts or when it stops. In fact, it could be starting and stopping in between requests without us even knowing, because the hardware is managed by AWS. We can't remove the factors that could skew the results of a comparison. Further, because of that, we decided that Chimera would not use comparison-based analysis and would instead use a threshold analysis. So Chimera just determines the health of a service by simply comparing the metrics to those user-defined thresholds. So now that we've talked about some of the design decisions, we're pretty happy with how Chimera has turned out, but there are some features that we would like to add in the future. For example, in its current state, Chimera can be used as a part of a typical CI/CD pipeline. But when the build phase is complete, Chimera has to be manually run to actually deploy the result of that build phase. So we would like to extend Chimera so that the user can actually set up automated Canary deployments that occur in response to some event. For example, pushing a Docker image to some kind of image repo. Another feature we would like to add is to add webhook features to Chimera so that the user could provide a webhook URL, and that would allow Chimera to send deployment status notifications to that URL. And this would allow Chimera notifications to be sent to a Slack channel, for example, or some other tool that could keep the team updated on the status of the deployment. So that is Chimera. Thank you for attending the presentation, and we'd be happy to take any questions you have. Okay, I'm not seeing any questions. Oh, there we go. There's a question. Okay, so what unique challenges are there for deploying a Canary into a microservice service mesh context as opposed to for a standalone app? So I guess what we're asking is there what particular challenges are there when we're talking about these containerized microservices versus a standalone app that doesn't have to be containerized and run on ECS or something like that? Anybody want to take that one?
Yeah, sure.
Yeah, I can.
Okay, go for it, Trevor.
Thanks. Yeah, I think one of the biggest additional challenges with having the larger infrastructure is the inter-service communication, which in Chimera's case is the AWS app mesh. It just adds a couple more layers of moving parts that have to be automated and a few more places that things could break that we'd have to watch for.
Yeah, I would say and I would add, it's with a single if you have like a monolithic application, you don't have to worry about, for example, say you have in a microservice architecture, say you have one team that's updating one service and another team's microservice depends on that one. That is a challenging part of doing these kinds of deployments, because one team's service may be getting failures that don't stem from the service they're actually responsible for. And so doing canary deployments like this could allow, you take advantage of the service mesh to deal with that. So unless anybody else has anything else to add, we have another question. It's why is Envoy necessary? And does the user of Chimera have to add it to their ECS task definition? Okay, I'll answer this one. So the Envoy is necessary because that's how App Mesh works. The Envoy proxies are actually what handle the inter-service communication for App Mesh, so that they're known as the data plane. And that's just the Envoy is just an open source tool. That's just what App Mesh uses. And the second part of your question is the user does have, when you set up a service mesh on ECS, you do have to update your services task definitions manually to include that Envoy proxy, but it's just a configuration property on that task definition.
But I'll add, because there's a few ways to interpret this question, is the user doesn't have to do anything during the Canary deployment. Chimera will automatically do that. We'll add the Envoy.
Okay, it looks like we don't have any other questions. Again, thank you all for attending. I hope it was at least interesting and that you enjoyed it.
Yeah, thank you.
Thanks, everyone.
Thank you, guys.